Good afternoon, everyone. This is Joe Steele. I'm the Communications Director here at LIFT in Detroit. Thank you very much for joining us for the June edition of the LIFT Off webinar. This webinar series is a partnership between LIFT and the Michigan Manufacturing Technology Center, which you'll hear about a little bit more later, and actually all of today, because today we're very happy to be talking about a project, a collaborative project that both LIFT, MMTC, and some other partners have worked on over the last couple of months. We've referenced it in a few other webinars, but today we get to talk about it a little bit more in depth. So very excited to be able to bring that to you today. A few housekeeping items before we get started. Again, please put your phones on mute. That way we won't have any background noise or interruptions during the presentation. If you have any questions, please use the chat function that is part of the GoToMeeting, and you can address that where it says to. You can address that to the organizer. Those questions will then come to me, and I will facilitate Q&A when the presentation is complete. As with all of our liftoff webinars, this session is being recorded, and we will post it on the LIFT website for future viewing. So if you wanted to share it with a friend, or if there were people who were unable to make it for one reason or another, they can always come back to the website and review it, watch it again, or check out some of the other presentations that have happened over the course of the past year. So a little bit about LIFT. We are part of a larger organization called Manufacturing USA, a network of 14 innovation institutes, all of them public-private partnerships, and all of them focused on R&D in a particular technology. Ours happens to be lightweight metals research, and we also focus on education and workforce. So our mission really is to revolutionize lightweight metals manufacturing through innovation and education. We are based here in Detroit, and we look to accomplish that mission in really 3 different ways. Technology development, like we just talked about, the R&D space that we work in. We have a number of technology projects that are underway across our network of industry members and academic members. We also work to transition that technology, because what good is innovating a new technology if we don't help transfer it into the marketplace? And then finally, education workforce development. All of us have heard about the skills gap that exists, the number of jobs that are available and will become available over the next 10 years. And frankly, there are just not enough people with the skills and abilities to take those jobs. So we're looking to expose students as early as middle school to the world of advanced manufacturing, as well as provide upskilling opportunities for the current workforce. One thing of note about LIFT, we have a new CEO and executive director on board here just within the past week or so, and name is Nigel Francis. So you'll be hearing more about him as he grows into the position. We really and he gets out there a little bit more and more. I did mention that we are here in Detroit. We have a lightweighting facility that is here. We are co-located with IACME, one of the other manufacturing institutes. They focus on composite materials while we focus on metals. But we do share space here. We have a 100,000 square foot building here in Detroit with an 87,000 square foot high bay innovation area, where it is there's metalworking equipment as well as composite equipment. So what you see on the screen is some of the equipment that we have available for you to use to help you continue your own R&D work, or help you scale a product up. We'd be certainly happy to talk to you about that. We have a number of services that are available with our in-house and network experts and engineers. Would be very happy to speak with you. You can reach us at the website lift.technology, or you can give us a call here at our building in Detroit. As I mentioned, we put on this webinar series with the Michigan Manufacturing Technology Center. The Michigan Manufacturing Technology Center is part of the MEP network, the Manufacturing Extension Partnership, through the National Institutes of Science and Technology out in Washington, D.C. They are our MEP partner here in Michigan, and they support manufacturers of all kinds not just in the lightweight metal space in which we operate, but they also support manufacturers with things you see on the screen, from cybersecurity to leadership development to they work in food, as a matter of fact. So anything that a small and medium-sized manufacturer would have to deal with, they certainly provide the assistance to do so. So here in Michigan, please reach out to MMTC. They're based over in Plymouth, so not too far from us here in downtown Detroit. You can reach them at their website at thecenter.org or the phone number that is on your screen now. And with that, the Manufacturing Extension Partnership, in collaboration with the Manufacturing USA Institute, each have embedded an engineer at the Manufacturing USA Institute. So we are happy to have Greg Peterson, who is our embedded engineer from the MMTC, with us on staff here at our Detroit-based facility, and we are happy to have him present a little bit more about the lightweight frame project that we have worked on together. So with that, Greg, I will turn it over to you to talk about the lightweight frame.
Well, first of all, I'd like to thank Joe and the LIFT team for the opportunity to present a lightweight frame that we developed. Our thought process was we wanted to make sure that we could utilize LIFT thermomechanical processing as part of this design, as well as assist small and medium U.S. manufacturers. So what I'm going to be talking about is pretty much a big break from what you traditionally do in the aftermarket. What happened is SEMA, the Specialty Equipment Manufacturing Association, lobbied for legislation permitting turnkey replica vehicles to be sold. So what this meant was you could fly to Boston, take a Uber over to Factory 5, jump in your 600 plus horsepower 427 Cobra and drive it home, instead of spending 4 or 5 years working on it. SEMA estimates that over 1,000 cars per year can be sold, and we've talked to a lot of the suppliers in this industry, in the replica car industry, and they think that they can increase their sales by a factor of 10 if they can sell completed vehicles. Now, the legislation limits the number of cars to 325 units per company, so there's still some things to be worked out. And if you do the simple math, you'll see that I'm using about $100,000 per car for these replica cars. And if you haven't looked at a replica car recently, they're becoming works of art. We're working with one company that's selling Corvettes, replica Corvettes, a base price at $250,000. So these things are not toys anymore. They're very well thought out vehicles. Okay, one of the things that we found out at SEMA and also from others is that a custom frame to support one of these vehicles can take 6 to 9 months to build, just one frame. So it can become a real bottleneck in this industry if you want to build a couple cars a day. So SEMA members, we were out there last fall just canvassing to see what they thought about our product, and they all expressed a need for a competitive contemporary frame. So there was definitely a market need. And not only the aftermarket, and I'll get into a little more detail on that, but also in the military. So lightweight in military has a big need as well, especially with the autonomous type vehicles that are coming on stream here, where you don't really need armor. They're kind of sacrificial, but if you can make them light enough, they become very agile and scout vehicles essentially. So the history of this, it was just a series of coincidences that got us to this point. I ended up meeting my Tennessee counterpart for IACME, embedded engineer at IACME, at an MSU composites workshop. And a company by the name of Dynamic Corvettes out of Saginaw, Michigan, one of their executives was there, and he said he couldn't get frames for his beautiful 57 carbon fiber Corvette, and asked if we could do this. And I had done similar work at Lotus, so I said, yeah. So we bounced it off of our management, and the center approved it, and then NIST subsequently approved it. So the center, we went out and solicited funding to get this going. We raised a total of $30,000 and more than $30,000 in kind, and I'll get into that a bit later. We did it in 3 months, and we do have a patent registered with the U.S. Patent and Trademarks Office, and it's primarily in the manufacturing area. Okay, these are the partners that we worked with. This was very much a team effort. We combined with Lyft, who did assembly and test support. We did the engineering lead and financial support at the center. IACME contributed all the carbon fiber engineering, and also contributed 1/3 of the funding to get us here. America Makes, which does additive manufacturing and 3D printing, were with us throughout in terms of supporting some of the work we're doing on the castings that I'll be talking about. And then the University of Tennessee Center for Industrial Services, Danny Norman there was instrumental in making all this happen through product development and management. Our collaborative partners that did the work, Dynamic Corvettes out of Saginaw, Michigan, a nationally known and highly respected company that has a lot of absolutely gorgeous Corvette restorations and resto mods, supplied technical and background support, parts, and actually built the MULE for us. Lumina Extrusion Council came on board. They contributed another 1/3 of the financial support and did the extrusion collaboration. Pennex just bent over backwards to help us. They were unbelievable in the support they gave us. They did all the extrusion engineering, material selection. They built the tool and manufactured parts that you'll be seeing towards the end of this presentation. And then another key company that really went over, just absolutely helped support us in more ways than we can even count. They did the scanning work, they did the CAD work, developed the FEA models, did all the crash work, and using their very innovative morphing engineering that's used to cut time frames from 6 months to less than a month for new body in white development, we applied that morphing engineering to our frame as well. And then lastly, Flash Steelworks, formerly Flash Bainite, did all the ultra high strength steel engineering for us, very helpful partner. So we're talking about hot rods here, sports cars, but we also are talking about specialty trucks. These trucks are really starting to get popular these days, and the frames are all rusted out. And it's not only the old trucks from the late 60s, early 70s that need frames, but also some of the newer vehicles like the late 90s Jeep Wranglers had some rust issues with their frames. So we've been asked to look into that. Doing specialty trucks, this frame can be a trailer as well. See it as really a helpful item for EV startup companies, where you have a lot of great technologists who know the drivetrain and batteries, but they don't really care what kind of frame they have. It's really kind of cumbersome for them to even try and do it. In the military, I've talked about the severe duty trucks and trailers, and then the electrified applications. A lot of autonomy going on there that the military is interested in. So the engineering targets, there's quite a few of these. First of all, we wanted to be able to fit the 63 through 67 Corvette body. That's one of the most popular Corvette body styles in the world. The cost obviously had to be competitive to these custom frames. Wanted to be lighter, wanted to be a lot stronger, and we also wanted to have a soft crash pulse. These vehicles do not have to be certified for crash. That was one of the things that restricted them in the past. But on the other hand, if you're spending $250,000 for a car, the first thing that your spouse is going to ask is, well, how safe is this compared to our Cadillac sitting out in the driveway? So we wanted to make sure that we address the safety aspect, which we don't believe any other frame manufacturer has done. No welding, that was very key. We wanted to be able to use existing shop personnel, and our objective is really to license this technology and then train the people at the various shops around the country that will eventually make this frame. The suspension, we used state-of-the-art suspension. The C5, C6, C7 Corvette suspension will bolt onto this. Use big tires, simple modular assembly. We also used KPCs, key process control points, on the castings that I get into a little bit later on. as our datum control so we could have consistent net builds so that every frame is exactly the wheelbase and length that you need. And doing that without fixtures, which add more cost. Low-cost tooling was a key part of this. Typically for a frame, an OEM can spend $5 to $10 million on tooling, and for us, this is a low-volume 1,000 unit per year target frame. It was going to cost us $1,000 a frame over a 5-year period to amortize traditional tooling. The tooling that we've selected, extrusions, pultrusions, and sand castings, and basically software control for some of the parts, allows us to amortize about $20 per frame over a 5-year period, a very affordable number. We wanted to make it easily adjustable over width and length with no tooling changes, so we could morph this frame from a small bug-eye Sprite to something as large as a big military JLTV type truck. We benchmarked some excellent cars, the Lotus Evora C7 Corvette. That's the Evora chassis on the left, and you can see the crumple zone. This is what aluminum extrusions look like after a 35-mile-an-hour frontal barrier test. They basically accordion. It's a very predictable, tunable aspect of aluminum extrusions that allows you to create a very safe frame very quickly and inexpensively. This is a C7 chassis as well. You notice both the Lotus and the Corvette are chassis rather than frames. And then lastly, powertrains can go anywhere from an LS3 430 horse to an LSA 556 horsepower certified engine. General Motors has certified these with the EPA specifically for the aftermarket. So you can do your 0 to 60s in 3 seconds or so with these cars and be fully emission legal. So the engineering process, we started out, we scanned a production C2 Corvette frame that was supplied by Dynamic Corvettes to establish the key hard points for the body, chassis, and powertrain. We wanted to make sure that we used our lightweight frame to match the key hard points on the existing frame so that a Corvette C2 body and actually a C3 body, 3rd generation as well, will bolt on to this frame. The next thing that we did was establish the baseline bending and torsional stiffness, and then we iterated the lightweight frame to meet our targets, which were much stiffer and lighter. And then we evaluated the frame for a military vehicle, an 18,000-pound gross vehicle weight truck at 5G vertical load. So what this means in plain English is that we applied an 80,000-pound uniformly distributed load to this little sports car chassis. And then lastly, we evaluated it for 35-mile-an-hour rigid barrier crash performance. That's equivalent of the MVSS 208. But again, this frame does not have to be certified. These replica vehicles do not have to be certified for any of the crash requirements for NHTSA. So the starting point, we took the frame delivered by Dynamic Corvettes and scanned it at DEP. So the DEP team set this up in their facility. In the background, in the upper left-hand corner of that room, you can see the Corvette suspensions, front and rear suspensions that we also scanned to make sure that we could allow clearances for the suspension travel. So we took the scan data, created a CAD model, and then created a finite element model by meshing the CAD data. So this is a real-time bending and torsion test. You can see the frames dynamically displacing there, and you can see the torsion is fairly high, and also the bending, you can see that bending, that's about 3.4 inches of displacement during bending. So this was an excellent frame, but it was an excellent frame 60 years ago. So it's relatively easy target to overcome and generate the numbers that we wanted to target. So what we did basically was engineered our frame, and then we overlaid it to make sure we got all the hard points right. So then we basically engineered our frame, and you can see this is another dynamic analysis for torsion and bending. The torsion was only 150% stiffer than the baseline, but the bottom line there is that with a frame, because you have very little height, it's difficult to make them stiffer. The way you make them stiffer is by putting bodies on and making sure that you have stiff bodies. And when we put a carbon fiber body on this, similar to the replica vehicle that Dynamic Corvettes is engineered, we hit 27,000 Newton meters per degree, which is equivalent to some of the 200-mile-per-hour Lamborghini supercars running around. So this is essentially a very stiff chassis. Weight-wise, we reduced the weight by about 90 pounds, so we exceeded our 30% target. And in this frame, I'm going to walk through these kind of one by one. The front bumper is made out of 6082 aluminum that Pennex developed for us. The rear bumper is the same 6082. The front rails and rear rails are 6063 aluminum that, again, were supplied by Pennex. Now, one of the things that we did, because we wanted to minimize the tooling costs, is we used one tool for every extrusion. So we iterated to the height we needed to get to the point where we could use one tool to make every single extrusion for the complete vehicle. So front and rear both use 100 by 100 millimeter extrusions. They're 1.5 millimeter wall thickness. Moving rearward, these castings are magnesium in the sports car version and aluminum in the military version. The cross members are carbon fiber protrusions, where you take basically a high matrix carbon fiber and pull it through a die. Very inexpensive to do. For the rockers, these are carbon fiber as well. What we do is we take two of the transverse cross members, glue them together, rotate them 90 degrees, and then cut them the appropriate length for the rockers. And then the rear castings are, again, the same material, magnesium or aluminum, depending on the application. And then lastly, we used ultra-high-strength steel for all of our brackets and for the front and rear cradle. So the engine sits on steel, rear suspension lower links and front suspension lower links both are attached to steel. The way that this goes together, this is the DEP analysis of our assembly. So you see the sequence, very simple, very modular. Our target is 2 people, less than 2 hours, and we can train people to be experts in this in less than a day. Once this frame is assembled, there's no priming, there's no painting. The metal parts come in powder coated, everything else is anodized, treated before it comes in. Now we're creating a giant battery here, so we do have nylon bushings that we use to isolate the different materials. So the steel from the aluminum from the mag. And this is a 3D printed right rear node that we did and have that on display as a learning part for us. This is the 18,000 pound severe duty truck frame. This falls into the GLTV weight category. And you can see, if you look at it carefully, you'll see that the castings are common here. We did not change them. Every other part, all we do is just trim to different lengths. So we can make anything from a 100-inch wheelbase to a 180-inch wheelbase vehicle without changing any of the tooling for this product. So everything is essentially common here, just trim to different lengths. So we trim the protrusions and we trim the extrusions to match the exact requirements. So this thing can be anything from a 80-inch bug-eye Sprite to a 180-inch military vehicle. So one of the things I mentioned, safety was a priority for us. And the reason that that was is because if you look at the crash test from many years ago, this was the oldest that I could find, 1959, and this frame was carried over into the early 60s. So this frame that I'm showing you, can everybody see this video?
Yes.
Okay, so what you're looking at is a 1959 Chevy Bel Air, their full-size car, versus a 2009 Malibu, 50 years apart. But you can see that the tremendous displacement that these two cars have, and the door is basically ripped off of this car. And you'll see the instrument panel on the 59 Chevy and one of the subsequent motion displays here, where the instrument panel moves a lot. So the bottom line is that the driver basically would not have survived this crash in the 59. And watch the instrument panel here. You can see the tremendous motion driving into the driver. And that's what happens with these older vehicles. And this really isn't something we want to be part of the frame that we're going to provide for people in replicas. So this is looking at it from the opposite version. It's a little scary seeing a car coming at you at these speeds, but you'll see the instrument panel doesn't budge on the Malibu, the air driver. And the only damage done to the occupant in the Malibu would have been in the foot area, and it would have been, it looked like fairly minor damage. But the Impala just is ripped apart. So this is the kind of technology that we were replacing, the 59 Impala, that type of technology. So essentially what we did was created a frame that would crush very easily. And I'll let this repeat a few times, but essentially if you look at the plan view,
Where's it going?
yeah, there. Yeah, just may have to drag it down.
Keeps moving.
Okay. So I'll just move on to the next slide here. But that video shows that we had a relatively soft crash pulse, about 20 G's average, which is in certainly the easily survivable range. The next thing that we did was basically built a MULE unit. This was based on a C7 Corvette. You can see the 10X extrusions there at the front and rear of the bumper area. And we ended up showing this at the 2018 SAE World Congress frame. This was with our partners, the Aluminum Extruders Council, who generously allowed us to display there. So this had, again, the 10X extrusion shown on it. The insert there shows some of the carbon fiber that went into this. So there's been a lot of press on this. These are links that you can go to and read articles about it. The latest article was published in Lightweighting World, and that is an extensive 8-page overview of the frame. So there's a lot of very good detailed information in there. So now I'm going to turn it over to John Keel. John's been doing some work on this at the lift in terms of testing adhesive bonding with the aluminum structure. So John, take it over.
Thank you. Thank you. Hello, everyone. Thanks for joining us today. So as you noted, I'm from LIFT here. I'm our development engineer, and you guys are all quite familiar with LIFT, and you can kind of see here on the screen the various facilities we have at our disposal. The role that I've played in this project here has to do with evaluating the bonding strength that would be associated with the front and rear bumpers and the front frame rails. You can see the Pennex extrusions at the bottom there as our starting material. And so the front and rear bumpers, as well as the front frame rails, are composed of trimmed pieces of those that have been bolted in a through-bolt way, or a through-bolt manner, and also adhesively bonded in between the joints there. So as Greg noted earlier, it's built with thin wall, 100 millimeter by 100 millimeter extruded tube. And so then in order to increase the bonding strength in between the components, surface pre-treatments are advised. So obviously, like normal, if you're going to put glue on something, you want to make sure that it's a clean surface. So you start out with an alcohol wipe, but then we also employ what's called plasma cleaning or plasma treating. But really, in order to validate it and make sure that it's worth using and see what benefits are associated with it, we needed to do some experiments. So what we did was we took some samples from the Pennex extrusions, and we set up two groups of bonded pairs. So one group being native, just alcohol cleaned, and then the other being alcohol cleaned and plasma treated. We took the samples, cut them to length, machined them, and then prepared them. And for the test group, or the experimental group, we employed plasma cleaning, and then for both groups, then the application of adhesive occurred, and then we clamped the components together, giving about 100 millimeter square or 100 times 100 millimeter square area of bonding. And then once cured, we went ahead and pulled the extrusions apart to see what sort of shear forces are needed to separate them. So we're going to show you a video here really quick of plasma treatment in action. So you can see behind there in the yellow, that's a FANUC robot that this plasma treatment head is mounted on. And there are a number of these test components that are all lined up in a line. So if you kind of look a bit off to the right there, you can begin to identify some of the lift there that's associated with our machine parts. Let me see if I can get this over here. There we go. Okay, so hopefully you can see it going back and forth right now. We basically set up the robot to employ a roster pattern going back and forth. And what this plasma treatment does is it activates the surface. It cleans, but also activates the surface so that way you get a stronger connection between your bonding agents and your material or your substrate. So I'll go ahead and play it one more time just to drive the point home. You can see that it's a rather quick process, actually. Plasma treatment is used also for enclosing headlights and assembling clamshells, things like that. So you can use it on metals as well as plastics and a variety of materials. The other head there that has the red component on it as well is also for plasma coating, which may serve a purpose in the future for this project because it also helps to inhibit electrochemistry and also protect surfaces. But for the purpose now, we're looking at the advantage of plasma treatment towards bonding. And so with that, we'll scoot on to the next slide. So you recognize this on the left side there. That is our load frame that we use to read out how much force it takes to separate the components. So you can see in the middle there that's a separated sample after it's been bonded and pulled apart. And then on the right, you can see about an 8 kilonewton force is required to separate that bonded surface area for an untreated sample. And then about 14 kilonewtons are needed for separating the plasma treated sample. So taking that data and with our two populations of treated and untreated bonded pairs, we ended up with approximately a 20% increase in the strength of the plasma-treated bonds. In the future here, with further testing, we're going to set up and do some peel tests because that's expected to show actually a greater difference than just a shear test that would pull them apart. And a peel test is more appropriate for these types of situations and the forces that the bumpers and the front sections would encounter in a crash scenario. But the take-home message here is that we have an approximately 20% increase under these tests for the strength of plasma-treated bonds. It really means then that to normalize things back out, you need to use approximately 20% less adhesive. So that keeps the car lighter and also keeps the cost down. And then also, I guess another take-home facet to it is that plasma treating is an important component of lightweighting to the application of structural adhesives because once again we can reduce the amount of adhesive that we have to employ. It doesn't show it clearly there that well at the bottom of these bars, but just for your information, the sample size for each one of these populations is 4, and so that's part of the reason why you see a good bit of standard deviation there. But nonetheless, though, it's well known that plasma treating is beneficial and really quite impressive. So, with that.
All right. Yep, just a couple more comments. The work that John did was completely done at LIFT using LIFT facilities. So the plasma treat lab is here at LIFT. The metrology lab where John did the Instron testing is here. So just very under one roof, you can do this. We also had a machine shop that trimmed all the parts here and did all the through bolting. One thing I neglected to mention is that the frame is completely adhesively bonded, but it's also through bolted so that we have both belts and suspenders. One of the things that John just showed you is that adhesives will unzip. So you need to have mechanical fasteners to stop that. But the combination of both of those provides just incredible strength. Lotus has been using this process for over 20 years now, and they have yet to have a single field failure with a rib bonded structure, aluminum structure. So with that, we thank everyone, and we'll certainly be open for questions.
Thank you.
Sure, thank you. Thank you, Greg, and thank you, John, for that. A couple questions came in. The first is, can you talk about how do you economically produce the node castings that you referenced in low volumes, particularly when you're talking about doing so in aluminum or magnesium?
Yeah, very good question. And that we chose sand castings as they're the lowest cost method of doing this. We considered additive manufacturing, but they're quite expensive. So the process that we're looking at is sand casting and using an ablation process to do that. Ablation casting basically means that you super quench the materials. So you take the part, you pour the material in, you have a reservoir with liquid molten metal that feeds the cavity. You ablate the sand off the front of the casting as it goes through, and essentially you super quench it. So you get forge-like properties with an inexpensive sand casting. The current Acura NSX uses sand castings, ablation sand castings, for their 190 mile an hour supercar. So this process has been under development for a long time, and it came out of Ohio State University, and it's now being utilized in industry.
Excellent, thank you. John, regarding the bonded piece, the red bonded area that we showed here did not completely fill the plasma treated joint. Won't that lead to corrosives getting in there?
That's exactly correct. Yes. So these were test samples that will, in application, will actually end up using a different adhesive and a different assembly method. Albeit an extrusion typically has quite good dimensions, these square tubes do have a bit of a bow inward, and so when you put them in contact, they really need to be clamped from the internal surfaces inward to make sure that there's good contact. So that probably also contributed to some of the standard deviation. But further studies that we're going to do, we actually really want to start out with, we want to do a study that involves not only plasma treatment, but also the area that is bonded. Because if we investigate, say, one line of adhesive versus 2, 3, and 4 lines of adhesive, at some point you are going to approach complete coverage, and that we'll see kind of an asymptotic relationship regarding how much adhesive is used and really the bond strength. But also, too, I guess to get back to the point there, yes, the manner in which the adhesive is applied, whether it's around a perimeter or whether or not the perimeter is properly sealed, is very important to consider, because yes, corrosives can ingress and salt from the road, things like that. So that would have to be something that is paid attention to in real production, and also is something that needs to be flushed out a little bit better for subsequent experiments. Yeah,
just to add to that, the intent of the adhesive is that it also, in addition to serving as a bonding agent, also serves to keep out contamination from water and dust, dirt, debris, etc. So that was not really a part of this initially, but it certainly is part of the longer-term development that we'll be doing here, that John will be doing.
Absolutely.
Thank you. Sticking to the corrosion theme, is the trimming of the extrusions, is that done before or after the surface treatment, including the anodizing and painting? If it's done after, how are the corrosions dealt with, or the potential for corrosion dealt with?
Yeah, very good question. And there would be some local after treatment just to make sure that at any of the cut areas that we have adequate protection. So very good point. But it's most economical to do the surface pre-treatments in bulk rather than by part. So that's at least our current thinking, is that it's more economical to do post-treatment than it is to bring the parts in, trim them to shape, then ship them back out and have them brought in again. So at this point, our thinking is just the shipment cost alone would make it uneconomical. and make it much more economical to do it in-house after you cut the parts.
So the treatment's done beforehand?
Well, the treatment is done beforehand, before the parts come in, but the point was that locally you're going to get erode away or cut away and expose some raw metal to potential galvanic issues. Right. So you need to locally treat that area.
Which is probably done by the assembling.
Yeah, it'd be something as simple as just a wipe with
right.
element.
Can you, Greg, go over the top line key metrics in terms of the improvements that this frame has, the reduction in weight and things like that one more time?
Sure. We reduced the weight by 89 pounds, so that was a 33% weight reduction. We increased the bending stiffness by a factor of 4.5. The crash safety, we have a crash pulse of about 20 Gs. The cost is actually very competitive with steel frames. And the reason is because of the way that we're putting this together using very little labor, the modular assembly. We cut the time by at least a factor of 20 compared to typical jig-mounted frames that are steel frames that are welded by skilled welders. It takes typically 40 hours or more to make one of the jig welded frames that I showed you in the beginning of this.
Thank you very much. Again, if you have a question, please use the GoToMeeting taskbar on the right-hand side of your screen. We have a couple more minutes. But I think that may be it for the questions. So as Greg and John, certainly appreciate your time. This is, again, an exciting project that we've talked a lot about, so I'm glad we had the opportunity to present it today. And again, if you have questions for Greg, you can reach him via the information you have on the screen there. You can reach out to John or anyone here at Lift through our website at lift.technology. So please go ahead and do that. And then stay tuned. Remember, look for your email. Stay tuned to your emails for next month, July 19th. We're always here on the third Thursday of each month at noon Eastern time. We'll be talking about rotational friction welding and the process that Coldwater Machining Company has. So please stay tuned for this. This webinar will be posted on our website probably Monday. And so you can take a look at it there. Go to the on the technology tab of lift.technology, and there's the liftoff webinar section under that. So please stay tuned and to your emails, and we'll talk to you in July. Thank you very much.